Dear students, very good morning to all of you. We will continue with Fourier series. This is lecture number 2. In this lecture, we will learn how to derive the orthogonality conditions of sines and cosines, how to derive the Fourier coefficients and solve some problems based on Fourier series. And lastly, we will discuss Parseval's theorem. First, orthogonality condition. To show that integral from 0 to capital T sin of n omega t dt is equal to integral from 0 to capital T cos of n omega t dt is equal to 0. So let us first evaluate the sine integral. Now, which is 0 to capital T sin of n omega t dt. Now we apply the rule of integration. So this is equal to minus 1 by n omega into cos of n omega t. Lower limit is 0 and upper limit is capital T. So this becomes equal to minus 1 by n omega. Now we substitute for the upper limit. So this becomes cos of n omega capital T minus cos of 0 if we substitute for the lower limit. Then this integral becomes equal to minus 1 by n omega into cos of n into twice pi minus 1. Now we have substitute twice pi for omega t because omega t is equal to 2 pi. So therefore we get minus 1 by n omega cos of twice n pi minus 1. Now we know that cos of twice n pi is equal to 1. So this expression becomes equal to minus 1 by n omega into 1 minus 1. So therefore this integral becomes equal to 0. Similarly, we can evaluate the cosine integral. So we apply the integration rule for cosine. So this becomes equal to 1 by n omega sine of n omega t, lower limit 0, upper limit is capital T. So this becomes equal to 1 by n omega into, we substitute for the upper limit. So this becomes sine of n omega into capital T, which is the upper limit, minus sine of 0 if we substitute for the lower limit, which is equal to 0. So therefore we get this integral equal to 1 by n omega into sine of n into 2 pi minus 0. Again omega t is equal to 2 pi. So therefore we get the value of this integral is equal to 1 by n omega into sine of twice n pi. Again sine of twice n pi is equal to 0. So therefore this integral also becomes equal to 0. So these are some useful formula which you should remember. Integral sine of nt dt is equal to minus 1 by n cos of nt. Similarly, integral cos of nt dt is equal to 1 by n sine of nt. Cos of n pi is equal to minus 1 to the power n and sine of n pi is equal to 0, where n is an integer. Second orthogonality condition. To show that integral from 0 to capital T sine of n omega t sine of m omega t dt is equal to capital T by 2 into delta n m, where delta n m is called the Kronecker delta function, defined as delta n m is equal to 1 if the indices n is equal to m, otherwise it is equal to 0. Now let us first evaluate the integral for the case n is equal to m. Now we substitute n is equal to m. So therefore we get the value of this integral. Let us denote this by capital I, subscript 1. So this becomes equal to 0 to capital T integral sine of n omega t sine of n omega t dt. So this is equal to integral from 0 to capital T sine square n omega t dt. Now we apply again the formula sine square n omega t is equal to half of 1 minus cos of twice n omega t. So therefore if we integrate this, we get this is equal to half of capital T minus 1 by twice n omega sine of twice n omega t, lower limit 0, upper limit is capital T. After we substitute for the lower limit and the upper limit, we get the final expression of I1 is equal to capital T by 2, where T is the period. Now we evaluate the integral for the case n not equal to m. So here we apply the formula sin a into sin b is equal to half of cos of a minus b minus cos of a plus b. So applying this formula, we get this expression is equal to this much, and now we solve this integral. So after solving this, we get the value of the integral I2 is equal to 0. So when n is not equal to m, then this integral is equal to 0. So therefore I1 and I2 can be combined to write 0 to capital T sin of n omega t sin of m omega t dt is equal to capital 2 by t by 2 delta nm, where delta nm is called the Kronecker delta function, defined as delta nm is equal to 1 if n is equal to m, it is equal to 0 if n is not equal to m. So these are some useful formulas of trigonometry, which is first one is cos of a plus b, it is equal to cos a into cos b minus sin a into sin b. Similarly, cos of a minus b is equal to cos a into cos b plus sin a into sin b. Sin 2 theta is equal to 2 sin theta cos theta, and cos 2 theta is equal to 2 cos square theta minus 1. This is also equal to 1 minus 2 sin square theta. The third orthogonality condition, to show that integral from 0 to capital T cos of n omega t cos of m omega t dt is equal to t by 2 into delta nm. Now let us first evaluate the integral for the case n is equal to m. So we put n is equal to m, therefore we get this integral equal to 0 to capital T cos square n omega t dt. Let this be equal to I1. So now we apply the formula for cos square n omega t. This is equal to half of 1 plus cos of twice n omega t. And now we solve this integral. If we solve this integral, we get the value of I1 is equal to t by 2. So therefore, for n is equal to m, we get the value of the integral equal to t by 2. Now we evaluate the integral for the case n not equal to m. Now in this case, again we apply the formula cos a into cos b, which is equal to half of cos of a minus b plus cos of a plus b. And after we solve this integral, we get the value of it is equal to I2 equal to 0. So therefore I1 and I2 can be combined to write 0 to capital T cos of n omega t cos of m omega t dt is equal to t by 2 into delta nm, where again delta nm is called the Kronecker delta function, defined as delta nm is equal to 1 if the indices are equal, else delta nm is equal to 0 if the indices are not equal. Now this is a very simple integration which we will require to remember. This is already we have come across in HS class. So this says that integral of u v dx is equal to this is the u is the first function, v is the second function. So this is equal to first function into integral of the second function minus integration of the ddx of first function into integration of the second function of dx. Finally, remember this formula. This will be useful. Also, we should remember that the average value of sine or cosine function over a complete period is equal to 0. That is, the average value of cos of an omega t, it is equal to 1 by t 0 to capital T cos of n omega t dt. This is equal to 0. Similarly, the average value of sine is also equal to 0. So therefore, our first orthogonality condition basically follows from this. So this says that 0 to t cos of n omega t dt is equal to 0. So this integral from 0 to t cos of n omega t dt is equal to 0. Similarly, the integral 0 to capital T sin of n omega t dt is equal to 0. Also, we should remember that the average value of sine square or cosine square function over a complete period is equal to half. So that means the average value of cos square n omega t is equal to if we evaluate this integral, we will get this equal to half. Similarly, the average value of sine square over a complete period is equal to half. Now let us prove the last orthogonality condition. So it says that 0 to integral from 0 to capital T sine of n omega t cos of m omega t dt is equal to 0 for all n. So now let us first evaluate the integral for the case n is equal to m. So if we put n is equal to m, then again this is nothing but sin a into cos b. So it is sin a into cos a. So this is equal to half of sin twice a. So now we solve this integral. After solving this, we get I1 is equal to 0. Now I1 is equal to 0 for the case n is equal to m. Now we evaluate the integral for n not equal to m. So now there should be an integral here, 0 to capital T sine of n omega t cos of m omega t dt. So this is a formula which we can write half of sine of a plus b plus sine of a minus b. So now if we evaluate this integral, then we get that this is equal to 0. That means for n not equal to m, this integral 0 to capital T sine of n omega t cos of m omega t dt is equal to 0. So this is for all nm, because in this case what we have seen that for n is equal to m also we have found that the value of this integral is equal to 0, as well as we have found that for n not equal to m the value of the integral is equal to 0. Therefore for all n m values, the value of this integral integral 0 to capital T sine of n omega t cos of m omega t dt is equal to 0. Now in the last class we have discussed about Fourier's theorem as well as Fourier series, and we have just derived this expression, but the evaluation of the coefficients were left. So in this class we will try to evaluate these coefficients a0, an and bn. So we know that the Fourier series of a single valued continuous or piecewise continuous periodic function f of t having t in the range 0 to capital T or t in the range minus t by 2 to plus t by 2, where t is the period, is given by f of t is equal to a0 plus summation over n is equal to 1 to infinity an sine of n omega t plus summation over n is equal to 1 to infinity bn cos of n omega t, where a0, an and bn are called the Fourier coefficients. Now let us first try to evaluate the coefficient a0. So we write down the expression for the Fourier series. Now we integrate both sides with respect to t in the limit 0 to capital T. So after integrations, this expression becomes equal to this. Now this integral will be nothing but a0 into capital T, and this one can be arranged as summation over n is equal to 1 to infinity. Now this integral will act only on the functions containing t, okay, which is sine of n omega t. So therefore this integral will act only on the function containing t variable. So therefore we can write down this expression as this plus the next expression, which is this one. So integral of this can be written as summation over n is equal to 1 to infinity bn integral from 0 to capital T cos of n omega t dt. Now we already know that the value of this expression is equal to 0, as well as the value of this expression is equal to 0. So therefore we get integral from 0 to capital T f of t dt is equal to a0 into capital T. So therefore a0 is equal to 1 by capital T into integral from 0 to capital T f of t dt. So therefore the Fourier coefficient a0 represents the mean or the average value of the function f of t in the interval 0 to capital T. We should remember that the mean or the average value of a function f of t in the interval t1 to t2 is given by average value of f is equal to 1 by t2 minus t1 integral from t1 to t2 f of t dt. Now we evaluate the Fourier coefficient a0. Now in this case what we do, we multiply both sides with sine of m omega t and integrate with respect to t in the limit 0 to capital T. So after we integrate this, then we get the values of the expression like this: 0 to capital T f of t sine of m omega t dt is equal to summation over n is equal to 1 to infinity an integral from 0 to capital T sine of n omega t sine of m omega t into dt plus integral from n is equal to 1 to infinity bn integral 0 to capital T cos of n omega t sine of m omega t into dt. Now we already have learned the orthogonality condition for sines and cosines. We know that this expression is equal to t by 2 into delta nm and this expression is equal to 0. So therefore what we get, the integral from 0 to capital T f of t sine of m omega t dt is equal to summation over n is equal to 1 to infinity an into t by 2 into delta nm. Now we know that the above integral will have a non-zero value if and only if n is equal to m, because it is only for these values this summation will basically contribute, only for n is equal to m. For n not equal to m, this will give rise to 0, because if n is not equal to m, delta nm is equal to 0. So therefore this above expression is basically it will contribute only for n is equal to m. So therefore substituting for n is equal to m, we get this integral equal to 0 to capital T f of t sine of n omega t dt is equal to an into t by 2. So therefore an is equal to 2 by t into integral from 0 to capital T f of t sine of n omega t dt. Now we evaluate Bn. Now in this case what we do, in order to evaluate Bn, we will multiply both sides with cos of m omega t and integrate with respect to t in the limit 0 to capital T. So after we multiply this and integrate with respect to t, we get this expression as like this, and this can be written in this form. So this is integral from 0 to capital T f of t cos of m omega t dt summation over n is equal to 1 to infinity an integral from 0 to capital T sine of n omega t cos of m omega t dt plus summation over n is equal to 1 to infinity bn 0 to capital T cos of n omega t cos of m omega t dt. Now already from the orthogonality condition we know that this integral is equal to 0, only this integral will survive. So this is equal to t by 2 into delta n. So therefore the integral from 0 to capital T f of t cos of m omega t dt is equal to summation over n is equal to 1 to infinity bn into t by 2 into delta n. The above integral will have a non-zero value if and only if n is equal to m. Therefore substituting for n is equal to m on both the two sides, what we get, 0 to capital T f of t cos of n omega t dt is equal to bn into t by 2. So from here we find bn is equal to 2 by t into integral from 0 to capital T f of t cos of n omega t dt. Okay, I leave this to you to solve. So kindly show it to me in the next class. The question says that the Fourier series of a single valued continuous or piecewise continuous static function f of x having x lying in the range minus L to L, where twice L is the period, is given by f of x is equal to a naught plus summation over n is equal to 1 to infinity a n sin of n pi x by l plus summation over n is equal to 1 to infinity b n cos of n pi x by l, where a naught, a n and b n are called the Fourier coefficients, so that the coefficients are like this: a naught is equal to 1 by 2 l integral from minus l to l f of x dx, a n is equal to 1 by l integral from minus l to l f of x sin of n pi x by l dx, and bn is equal to 1 by l integral from minus l to l f of x cos of n pi x by l into dx. Now Dirichlet conditions. Dirichlet conditions state that suppose fx is defined and single valued except at a finite number of points in the interval minus l to plus l. Fx is periodic with period twice l. Fx and f prime x are piecewise continuous in the interval minus l to plus l. Then the Fourier series f of x is equal to a naught plus summation over n is equal to 1 to infinity a n sin of n pi x by l plus summation over n is equal to 1 to infinity b n cos of n pi x by l, with coefficients a naught is equal to 1 by 2 l integral from minus l to l fx dx, a n is equal to 1 by l minus integral integral from minus l to l fx sin of n pi x by l dx, and bn is equal to 1 by l integral from minus l to l f of x cos of n pi x by l into dx. It converges to fx if x is a point of continuity. It converges to fx plus fx minus divided by 2 if x is a point of discontinuity. Here fx plus and fx minus denote the left hand and right hand limits of x respectively, given by fx plus is equal to limit x tends to x plus fx, it is equal to limit h tends to 0 f of x plus h. Fx minus is equal to limit x tends to x minus fx is equal to limit h tends to 0 f of x minus h. Fourier series for an even function. So the Fourier series for an even function f of x, we know that an even function is defined as f of minus x is equal to x for all x. So where fx is a periodic function with period twice l in the range minus l to plus l, is given by fx is equal to a naught plus summation over n is equal to 1 to infinity bn cos of n pi x by l. Now where a naught is equal to 1 by 2 l integral from minus l to l fx dx, a n is equal to 0 and bn is equal to 1 by l minus integral from minus l to l fx cos of n pi x by l into dx. Now here the integral a n becomes equal to 0 because this a n is equal to 1 by 2 l integral from minus l to l fx sin of n pi x by l into dx. Now fx here in this case is an even function in the range minus l to l, but sin of n pi x by l is an odd function of x in the range minus l to l, and we know that the integral of integral of the multiplication of an even function and an odd function in the complete range minus l to l is equal to 0. That is why a n is equal to 0. Similarly, for an odd function, we know that f of minus x is equal to minus fx. So therefore the Fourier series for an odd function fx, where fx is a periodic function with twice l in the range minus l to plus l, is given by fx is equal to only summation over n is equal to 1 to infinity a n sin of n pi x by l. Here a naught is also equal to 0 and b naught bn is also equal to 0 because we know that the integral of an odd function over the complete period is equal to 0. That's why a naught is equal to 0. Similarly, the integral of the product of the odd function and an even function is also equal to 0 over the range minus l to l. That's why bn is equal to 0. So here only the coefficient a n survives. So these results follow from this two simple laws. These are the integration of the product of an odd function and an even function over a complete period, that is 0 to twice L, or from minus L to plus L is 0. So if there is an odd function and if there is an even function, the multiplication integral of this multiplication is also equal to 0 all the time. And in other cases, the integration of let's say odd function, it will always give a finite value. Similarly, even function, it will give a finite value in the range 0 to twice L or from minus L to plus L. Now let us solve some of the problems based on Fourier series. Find the Fourier series of the given triangular wave. So the triangular wave is given, the wave is repeating, this piece of the wave is repeating in identical fashion. So therefore the period is t, because after this interval of time the same piece of the wave is repeating. So first of all we have to find out the value of the function f of t as a function of t, and for that we will apply a simple rule. This is the rule from coordinate geometry. We know that the equation of a straight line having x and y intercepts as a, capital A and capital B respectively is given by x by capital A plus y by capital B is equal to 1. Now if we apply this formula in our case, then we get t by capital T. Here in our case, instead of x we have t, and instead of this x intercept, what we have is capital T. Similarly, instead of y, what we have is here y is there is the same, y is equal to f of t, and the y intercept is your small a. So we get in our case small t by capital T plus y by a is equal to 1. So from that we find the value of y is equal to a into 1 minus small t by capital T, and since y is nothing but the function f of t, so therefore f of t is equal to a into 1 minus small t by capital T. Now we know that the Fourier series of a piecewise continuous periodic function f of t having period capital T is given by f t is equal to a naught plus summation over n is equal to 1 to infinity a n sin of n omega t plus summation over n is equal to 1 to infinity b n cos of n omega t. And these are the Fourier coefficients, because our range is 0 to capital T. So therefore we will write down the formula as a naught is equal to 1 by t integral from 0 to capital T f t dt, a n is equal to 2 by capital T integral from 0 to capital T f t sin of n omega t dt, and b n is equal to 2 by capital T integral from 0 to capital T f t cos of n omega t dt. Now we put the value of f of t here, and we solve this integral, and this comes out to be a by 2. So therefore this is the average value of the function f of t in the range 0 to capital T. You can see that this is the average value. So a by 2 will be lying somewhere here. It will be lying somewhere here. Okay. So it will be just half of this length. It will be lying here. So this is the average or the mean value of the function in the range 0 to capital T. Now we evaluate a n. So again we put the value of f of t here, so which is equal to a into 1 minus small t by capital T. So we solve this integral, and in order to solve this integral we will have to apply the formula of integration by parts, and we know the formula. Applying the formula for integration by parts, we get the value of a n is equal to a by n pi. Similarly, we evaluate the Fourier coefficient Bn. We write down the formula for Bn, which is equal to 2 by capital T 0 to capital T ft cos of n omega t dt. Now we substitute the value of f of t here, and we simplify this expression, and this comes out to be in two different parts. First part is equal to 0 because we already know that the value of this integral is equal to 0, and the second part is, it can be written as 1 by t integral from 0 to capital T t into cos of n omega t dt. Now t is an odd function, and this is an even function, and we know that integral of the multiplication of the odd function and an even function over a complete period is equal to 0. So therefore Bn is equal to 0 in this case. So therefore the Fourier series of the given triangular wave is given by, so we have evaluated the coefficients a0, an and bn. So after we substitute the values of a0, an and bn here, we get f of t is equal to a by 2 plus a by pi into sine of omega t plus half of sine of twice omega t plus 1 by 3 sine of twice of omega t up to infinity. So this is the Fourier series expansion of the given triangular wave. Now let us apply the Fourier series in the case of a square wave. Now for the given square wave, we can write it as a function of f of t. So in the range 0 to capital T by 2, f of t or y is equal to a, and from t by 2 to capital T, this is equal to 0. The value of the function is equal to 0. Alright, so now we apply the Fourier series formula. So this is the formula. We know what are the values of the coefficients a0, an and bn. So we will try to evaluate all these coefficients for the given function, and if we apply this formula for the given function, and we know that the given function has two parts, it is 0 to t by 2 and the other is t by 2 to t. So for the range 0 to t by 2, the value of the function is y, but for the interval t by 2 to plus t, the value of the function is equal to 0. So the value of the function is 0 here, and for the interval 0 to t by 2, it is equal to a. So we get a0 is equal to a by 2. Again, it is the mean or the average value of the function in the given periodic range 0 to capital T. So the mean value will be somewhere here, a by 2. So a by 2 will be this line. Now we find out, evaluate the coefficient an. So we know the formula for an is equal to 2 by t, 0 to capital T ft sine of n omega t dt. So again we put the value, we substitute the value of f of t, and we get the value of an is equal to a by n pi into 1 minus cos of n pi. Now cos of n pi is equal to minus 1 to the power n, so therefore an is equal to a by n pi into 1 minus 1 to the power n, since cos of n pi is equal to minus 1 to the power n. So there are two cases that we have to deal with. First case, n is an odd integer. If n is odd, then we will get this value to be equal to minus 1. So 1 minus 1 will be plus 1, and for even function it will be simply 1. So when n is odd, we get an is equal to twice a by n, and an is equal to 0 if n is even. So only the odd terms will contribute to the coefficient an. Now we evaluate the coefficient bn. So we write down the formula for bn. Bn is equal to 2 by t, 0 to capital T ft cos of n omega t dt. So bn is equal to, so we substitute for the values of f of t, and we simplify it. After simplifying, we find that bn is equal to 0. So therefore what we have seen, that only the odd terms of the sine series appear in the expansion, because cos terms do not appear because the coefficient bn is equal to 0. So only sine terms will appear in the Fourier series. So therefore what we have, f of t is equal to a naught plus summation over n is equal to 1 to infinity a n sin of n omega t. We substitute for the values of a naught, which is equal to a by 2, and now a n, it is it contributes only for the odd values of n. That means n is equal to 1, 3, 5 and so on. So, and for odd values of n, we know that a n is equal to twice a by n pi. So now the final expression of f of t becomes equal to a by 2 plus twice a by pi into sine of omega t plus 1 by 3 sine of 3 omega t plus 1 by 5 sine of 5 omega t up to infinity. Parsevals identity. It states that if the Fourier series corresponding to fx converges uniformly to fx having x in the range minus L to plus L, then we have 1 by twice L integral from minus L to L fx square dx is equal to a naught square plus half of summation over n is equal to 1 to infinity a n square plus b n square. Now let us prove this relationship. So we know that the Fourier series of a single valued continuous or piecewise continuous periodic function f of x having x lying in the range minus L to plus L, where twice L is the period, is given by fx is equal to a naught plus summation over n is equal to 1 to infinity a n sine of n pi x by L plus summation over n is equal to 1 to infinity b n cos of n pi x by L, where a naught, a n and b n are the usual coefficients. And we should note down that f of x plus twice L is equal to f of x, because here fx is a periodic function having period twice L. Now what we do, this is the equation number 1. So we multiply this equation with fx and integrate with respect to x in the limit minus L to plus L. So after doing that, we get the expression equal to minus integral from minus L to plus L f square x dx is equal to minus L to L a naught fx dx plus integral from minus L to L. This expression summation over n is equal to 1 to infinity a n sine of n pi x by L, and this is fx dx. So the last term is minus integral from minus L to L, this summation over n is equal to 1 to infinity b n cos of n pi x by L into fx dx. Now since this integral will only act on the term containing x, because the integration is with respect to x only, so therefore we bring the integral inside the summation where it acts on the functions containing x terms only. So this becomes equal to minus integration from minus L to L f square x dx is equal to a naught minus integral from minus L to L fx dx plus summation over n is equal to 1 to infinity a n, and this is integral from minus L to L fx sine of n pi x by L dx plus summation over n is equal to 1 to infinity b n into integral from minus L to L fx cos of n pi x by L into dx. Now we know that this one is already, we know that this is equal to how much, integral from minus L to L fx dx. This you can go back and see how much is that. So the integral from minus L to L fx dx is equal to nothing but a naught into twice L. So this is a naught into twice L. So this value of this integral is equal to a naught into twice L plus summation over n is equal to 1 to infinity. This is a n. What is the value of this integral? That means the integral from minus L to L fx sine of n pi x by L into dx. Let us go back, and this is equal to, it is a n into n. Okay, so you put a n into L for this integral, and the last integral is nothing but b n into n. So therefore the simplified expression now becomes equal to integral from minus L to L f square x dx is equal to twice L a naught square plus L into summation over n is equal to 1 to infinity a n square plus L into summation over n is equal to 1 to infinity b n square. So we divide both sides by 1 by twice L. So we get 1 by twice L into integral from minus L to L f square x dx is equal to a naught plus half of summation over n is equal to 1 to infinity a n square plus summation over n is equal to 1 to infinity into bn square. In the last class, one of you has asked me for some reference books. So these are some of the reference books which I follow, and out of all these 4 books, this is a very excellent book, first one and the last one. In the last one it has a number of problems, and for physical concept this book by Weber and Afken is a very good book. And similarly, for problem solving, you can also consult the book by Arvin Krajcik. Thank you.